Okay, so good morning and welcome everyone to another Lisbon seminar. So today we have the pleasure of having a seminar by Gernot Eichmann. Gernot is an FCT researcher working in the NPStrong group here at LEAP, and he has a sound research record on nonperturbative QCD. Today he will talk about quarks, gluons, and their relation with hadrons and multiquarks. So welcome, Gernot, and the stage is all yours.
Okay, so thanks for the introduction. It's a pleasure to be here. So I will talk about some of the research we're doing at NPStrong. Now, I assume that most of you are not overly familiar with this, so I will keep it to a basic level, but if you're interested in more details, then please just ask. So our research interests revolve around QCD and nuclear physics. We're interested in the quark-gluon structure of hadrons, what they are made of and how we can describe them from nonperturbative QCD. Even though the Higgs gives a mass to the standard model particles, we know that 98 to 99% of the mass of visible matter is generated in QCD. It's stored in the energy of the gluons, but how that mass comes about and how it is related to confinement is still an open question. And to study it, we have to study hadrons. There is more evidence for states beyond the naive quark model. So on top of the ordinary mesons and baryons, there could be glue balls and hybrid mesons, tetraquarks and pentaquarks. We're also interested in the phases of QCD, how hadrons dissolve when we switch on temperature and density. And finally, can we take our knowledge of QCD to also describe nuclei from the underlying quark and gluon degrees of freedom, and in that way maybe answer some of the outstanding questions in nuclear physics. So here is an overview of our research. We're working with functional methods, in particular Dyson-Schwinger and Bethe-Salpeter equations and the covariant spectator theory, which I will explain in a second. These are the topics we've been working on: meson and baryon spectroscopy, form factors, ab initio calculations, the muon G-2 problem, tetraquarks and pentaquarks, nuclei, the QCD phase diagram, resonances and scattering amplitudes, and hadron structure calculations. Now, this talk is not meant as a comprehensive overview of the research we're doing at NPStrong. I will mostly focus on the things I've been directly involved in. I will just give you some of the highlights of some of these topics. Here is one slide on the methods. That's Dyson-Schwinger and Bethe-Salpeter equations in a nutshell. If we're interested in bound states of n valence quarks or antiquarks, we solve such covariant bound state equations. They come with different names: Bethe-Salpeter equations, or Faddeev equations for 3 quarks, or Faddeev-Jakubowski equation for 4 quarks. The names are inherited from nuclear physics. If you're not familiar with this, maybe a good way to think about it is the quantum field theoretical analog of a Schrödinger equation. From a Schrödinger equation, you would get the energy and the wave function of a system. And from here, you get the mass of a hadron and its wave function, the yellow blob, which is the Bethe-Salpeter amplitude. So with this, we can do spectroscopy calculations. In practice, the equations are solved in momentum space. These are essentially Feynman diagrams. So every loop here is a 4-dimensional momentum integration. So this becomes a self-consistent integral equation. And the blue box here is the kernel of the equation. To solve it, we need to know what the ingredients are that go into this kernel. These are QCD's endpoint functions or green functions. For example, the dressed quark propagator is what happens to a quark when we switch on quantum loop corrections. And these are described by the Dyson-Schwinger equations, or DSEs, which are QCD's quantum equations of motion. One outcome of this is the dynamical generation of a quark mass. Here is the quark mass function, and I will talk a bit more about this later. At large momenta, we have the current quark mass that goes into the QCD Lagrangian, but at small momenta, a large constituent mass is dynamically generated. And this corresponds to the 98% effect that I mentioned earlier. Now, it's not sufficient to know the quark propagator. We also need to know the gluon propagator and higher endpoint functions like the quark gluon vertex and the 3 gluon vertex. They satisfy their own equations, which would back couple into the ones you see here. So in the end, this becomes an infinitely coupled system. Now the strategy is to start with the lowest endpoint functions, the 2-point functions, the 3-point functions, maybe also the 4-point functions, calculate them to good precision, compare, for example, with lattice QCD, and use them to calculate hadronic observables. Once we know the wave functions, we can also do structure calculations, for example, for form factors, in principle also PDFs, GPDs, TMDs, or 2-photon processes, or general scattering amplitudes. Now, an alternative way to treat these equations is the covariant spectator theory, which has been developed by my colleagues, Alfred and Teresa and Elmar, originally for few nucleon systems, but meanwhile, these are also applied to calculations in QCD. Now, we'll spend a few more slides on the endpoint functions because I think that's useful for a better understanding of what's going on here. The first point is that in a quantum field theory, everything runs. This may not be immediately obvious from the QCD Lagrangian or the classical action, which is the integral over the Lagrangian over d4x. I'm using a Euclidean metric here, so don't worry about that. These are just conventions. So what the Lagrangian tells us are the basic construction rules of the theory, that we have quarks and gluons, and that they interact in a particular way through quark-gluon interactions, a 3-gluon interaction, a 4-gluon interaction. But it doesn't tell us yet anything about the quantum field theory. This is what comes in through the path integral. When we integrate over all possible quark and gluon fields, we pick up quantum loop corrections. So in that way, our 3-level propagators and vertices become dressed. So the blobs here, for example, for the quark propagator, contain all possible ways how a quark can emit and reabsorb gluons, and in that way get dressed. And in that way, we can also generate higher endpoint functions like a quark-antiquark scattering matrix or a 3-quark scattering matrix, and in principle, infinitely many of them. Now, in particular, going from classical to quantum means we pick up structure. So for example, the quark from the Lagrangian is just this thing here. It's the Fourier transform of the d/+m. So there are 2 tensors here. One goes like p/, one goes like the unit matrix in Dirac space. When we go to the quantum field theory, this means that both of these structures will pick up, both of these tensors will pick up structure. So we have 2 dressing functions which depend on p². One of them is the quark mass function that I showed earlier, which encodes the running of the quark mass. Likewise, the gluon propagator in the Lagrangian is hidden in the f-mu term. If you work it out, you get this. When you go to the quantum theory, it picks up structure, a dressing function. Or the quark gluon vertex is just a gamma mu. It lives right there. When we go to the quantum theory, it picks up a dressing function. Plus, the quantum loop effect can also generate new tensors. Anything that is possible from Lorentz invariants. So for example, this here would correspond to the anomalous magnetic moment. So everything runs with the momentum. The quark mass runs with momentum. The gluon runs with momentum. The running coupling in QCD is a particular combination of these dressing functions and therefore runs with momentum. So this means the dressing functions of these objects encode everything we can know about quarks and gluons. So they encode the full quantum field theory. Now you might wonder how this connects to perturbation theory, because in principle we know how to expand scattering amplitudes and processes in perturbative loop diagrams. Well, the answer is that these are exact equations, so they generate every diagram in perturbation theory. So for example, here in the quark DSE, we have the inverse propagator on the left, the inverse 3-level propagator on the right, minus the self-energy. We can convert this into equation for the propagator itself instead of its inverse, which is still an integral equation. Now, if I take the full right-hand side and insert it again here in the propagator, I will generate a series. And if I do the same for all the ingredients of the self-energy, then I end up with all the perturbative Feynman diagrams in perturbation theory. So at 1-loop level, we have just the gluon dressing of the quark. At 2-loop order, the 1-loop correction of the quark propagator will produce such a rainbow diagram. The 1-loop correction to the vertex will produce a diagram like this. The 1-loop correction to the gluon will produce a diagram like that. And there are a couple of more of those. So from this point of view, it looks like a Dyson-Schwinger is just a convenient way to rearrange perturbation theory. But actually it is more than that, because it is non-perturbative. And a simple effect where this is visible immediately is dynamical mass generation. So I said that the quark propagator depends on two dressing functions. One goes with the p slash and one for the scalar part. This means if we take the trace over this, we will project out the scalar part. So we'll project out the mass function. So the mass function is proportional to the trace of the quark propagator, or also its inverse. Both statements are true. So if I take the trace over these diagrams, I will produce something that is proportional to the mass function. Now suppose we start with the massless theory. So I switch off the current mass in the Lagrangian. Then my tree-level quark is just this, p slash without the m. The quark-gluon vertex is still the same, gamma mu. And now let's put this in here. Then I have a quark-gluon vertex, gamma mu. Here I have a propagator, p slash gamma mu. So I have a product of 3 gamma matrices. The trace over an odd number of gamma matrices is 0. So this diagram will not contribute to the mass function. What about this one? Gamma mu, p slash gamma mu, p slash gamma mu, p slash gamma mu, which is again an odd number. So also here, no contribution. Same here, 1, 2, 3, 4, 5, 6, 7, also an odd number. So in fact, every perturbative diagram contains an odd number of gamma matrices. So we can never generate a mass function from that. And yet, when we solve the Dyson-Schwinger equation, even for massless quarks, we get a large dynamical mass function. So apparently we lost something when we went from the non-perturbative equation to the perturbative series. Dynamical mass generation is a non-perturbative effect. The analog of that would be the spontaneous magnetization in a magnet below a critical temperature. So here in this system, the role of temperature is played by momentum. So in a sense, you could think that below a critical momentum, you spontaneously generate mass. And that doesn't change substantially if we switch on the current quark mass in the Lagrangian, for example, 3 MeV for a light up and down quark, then we still have about 350 MeV coming from QCD on top of that. Eventually, this effect will be washed out if we go to higher current, if we go to more massive quarks. So for strange quarks or charm quarks or bottom quarks, because the contribution is always about 350 MeV that comes from QCD. The origin of this is the dynamical breaking of chirosymmetry, the spontaneous breaking of chirosymmetry. This is a dynamical effect that comes from the gluon self-interactions. Spontaneous symmetry breaking is always connected with massless modes, so we would expect some massless particles in a spectrum. And these are the pions. When we solve the Bethe-Salpeter equation for the pion, we see that the pion is indeed the Goldstone boson of the spontaneous symmetry breaking. So here I'm showing the pion mass as a function of the quark mass. At the physical point, it has a mass of 140 MeV. And as we switch off the quark mass and go to the chiral limit, the pion mass squared vanishes with the quark mass. The rho meson mass doesn't do anything like that, it just goes to a constant. So these three effects are connected. The dynamical breaking of chirosymmetry generates a large dynamical mass function. This is what goes into Hadron spectroscopy and structure calculations. This is what gives a large mass to the rho meson, or also to the proton and other hadrons. Whereas the pion remains light because it's the Goldstone boson in the chiral limit. Okay, so those were the foundations. Now let's come to the applications. I will start here in the left upper corner with Baryon spectroscopy. This is again the three-body equation, the covariant Faddeev equation. I just stretched it out so you can better see its structure. We have the sum of permuted two-body kernels plus a three-body interaction. Now it turns out that the leading irreducible three-body force, which is the 3-gluon vertex that connects the 3 quarks here, this diagram vanishes just by the color trace. So this already hints towards a dominance of the two-body correlations in baryons. What we usually do is use a rainbow ladder truncation, so the kernel becomes a gluon exchange with some momentum-dependent dressing function. This is a model that has been often used in the literature. It is constrained large momenta by perturbative QCD. At low momenta, it depends on two parameters, a scale that comes in through k squared over lambda squared, and that has to be matched to experiment, and a shape parameter that allows me to change the shape of this interaction at low momenta. But after that, there are no further approximations. So we include the full structure of this three-body amplitude, which is quite complicated. So the only input to this equation is the kernel here. And here you see how this plays out. So I'm showing the rho meson, the nucleon, and the delta mass as a function of the pion mass squared. So remember, the pion mass squared goes like the current quark mass. So this is the current mass evolution, starting in the chiral limit. Here are up and down quarks, here are strange quarks. And the bands are our results, and they correspond to this variation of the shape of this interaction in the infrared. You see that they are pretty narrow. So these masses are not sensitive to what exactly this interaction looks like at low momenta. The scale was fixed to the pion decay constant. So I solve the pion equation, calculate the pion decay constant, and then I match it to experiment. And that is sufficient to reproduce the nucleon mass. So here the nucleon mass comes out as 940 MeV, but there are no further parameters here. The points I'm showing here are lattice results, and also here we are in the same ballpark. Just to give you an idea of what this involves computationally, so this is the three-body amplitude. We have 3 independent momenta in the system. From those we can construct 5 Lorentz invariants and 64 tensors for the nucleons, so 64 Dirac tensors. You could think of this equation as an eigenvalue equation for a large kernel matrix. The dimension of that matrix grows with the number of variables, of momentum variables in the system, and with the number of tensors. So for example, for a two-body system like a meson, the kernel is typically a 1000 by 1000 matrix or a few thousand by few thousand matrix. For a three-body system, depending on how many grid points you put in there, it's already a million by million matrix, up to a billion by billion matrix. So you can imagine that this requires high performance computing and a powerful computing infrastructure. A simpler way to deal with the system is to go to a quark-diquark description. If we cluster 2 quarks in a baryon together to a diquark, we end up with a two-body system of a quark and a diquark. This can be derived from the three-body equation. So here is the quark-diquark wave function. That's the equation. It might not be immediately obvious from here, but when you iterate this, so when you take again the right-hand side, put it in here and iterate it, then what you generate is a ping-pong exchange. So one of the quarks ping-pongs between the 2 other quarks, and in the process generates diquarks. So the interaction here is a quark exchange. And again, one can calculate all the ingredients here in rainbow ladder, and in that way one can compare the quark-diquark and the three-body calculations directly. And here you see how they compare, and also how they compare with experiment. This is the nucleon excitation spectrum. So the red boxes are the PDG masses. The blue boxes are the quark-diquark and the 3-quark results. And you see the comparison works quite well, where such a comparison is possible. So here for the nucleon, for its first excitation, the Roper resonance, for the delta resonance, and also the comparison with experiment looks quite good. So this points towards a 2-quark or a diquark clustering inside baryons. Now the simplest structure observables are form factors. Here I'm showing the nucleon's electromagnetic form factors calculated from the three-body equation compared to experimental data plotted over Q squared. Also here we're doing a not too bad job. So the electric form factor of the proton is pretty much compatible with the data. For the magnetic form factors, we see discrepancies at low Q squared. If we compare this with chiral effective field theory, we can attribute these discrepancies to missing pion cloud effects. So essentially, the statement is that a rainbow ladder truncation generates the quark core of the baryon without the light meson cloud. that surrounds it. And we have found similar results for several other form factors, transition form factors, axial and pseudoscalar form factors, other octet and decubulate form factors. And most of this is collected in our review article from a couple of years ago. Now, to take advantage of having in principle an ab initio approach, we have to go beyond the rainbow ladder truncation. This means we also have to solve the Dyson-Schwinger equations for higher endpoint functions like the quark-gluon vertex or the 3-gluon vertex, which also reveals some interesting effects. And it turns out that this improves things quite a lot. So here you see, for example, the light meson spectrum for the different quantum numbers. Again, the red boxes are the PDG values. The gray boxes are the rainbow ladder results. Here for the pion and the rho, you don't see them because everything is on top of each other. And the blue boxes are the beyond rainbow ladder calculations. So it turns out that rainbow ladder really only works well for the pion and the rho. In all the other channels and also the excited states, they come out to light. But once we go beyond rainbow ladder, things fall into the right ballpark. So this tells us that we are on the right track. To get reliable results, we have to include higher endpoint functions in the system. That's also necessary to understand, for example, mass generation. This originated as a student project. Charles Silber was working on the gluon equation. Usually when we talk about mass generation, we talk about mass generation of quarks. But we also know that the effect already happens in the gluon sector. So to understand it, this is the place to look for it. This is the Young-Mills system, which means QCD without quarks. For these things, we also need a closer interplay between different methods, for example, the functional renormalization group and lattice QCD. The existing comparisons look quite promising here, for example, for the gluon propagator and the quark-gluon vertex. But there's a lot more that could be done in this area. Now let me briefly talk about the mu and G-2 problem. So the anomalous magnetic moment of the muon is one of the possible signatures for physics beyond the standard model, because currently we have a discrepancy, a 4 sigma discrepancy between the standard model prediction and experiment. The G-2 encodes the quantum corrections of the photons coupling to the muon. Here is a breakdown of the various contributions. The biggest effect by far comes from QED. All the QED loop diagrams have been calculated up to 5 loops. Then there are small electroweak and QCD corrections, but the biggest uncertainty here comes from QCD. So the standard model prediction, the theory uncertainty, is completely dominated by QCD. There are 2 diagrams here. One is the hadronic vacuum polarization, which is essentially the QCD dressing of the photon propagator, and which is well constrained by experimental data. And the other is the hadronic light-by-light scattering, the photon 4-point function, which is not so well constrained. There have been efforts to pin down the light-by-light amplitude using dispersion theory, which means by summing up intermediate on-shell mesons. So the leading term here is the 1 pion exchange, followed by 2 pion exchanges, etc. Now, to constrain the theory uncertainty, we have to understand the structure of these things, these form factors, the pion 2 photon form factor, transition form factor, and also the electromagnetic form factors of the pion and the kaon. So we had a couple of recent papers on that. For the pion transition form factor, we invented a method to extract the on-shell form factor from the off-shell one. This allows us to go to large Q-squared, which would be otherwise not possible. Here you see the discrepancy between the experimental Bell and Barbar data, and our result is on top of the Bell data. The second strategy to address this problem would be to calculate the hadronic light-by-light amplitude directly. This comes quite with a number of complications. It's a 4-point function, so it depends on a number of momentum variables and a number of tensors. Here we did a structure analysis of the light-by-light amplitude based on the permutation group S4, so we can arrange the momentum variables here into multiplets of the permutation group and figure out the important kinematic regions that contribute to the process. And here we also showed that there are 136 independent tensors within this object and not 138 as it was said previously. So you see the structure of these things becomes more and more complicated once we go to higher endpoint functions. The current frontier are 4-point functions like this. A similar object would be the 4-gluon vertex, and we're also interested in that. Okay, now let me come to exotic mesons and tetraquarks. I will spend some more slides on that. There has been quite some excitement on the exotic X, Y, and Z states in the germanium spectrum, some of which are candidates for 4-quark states. This started almost 20 years ago when the Bell collaboration found a surprisingly narrow state, the X3872, close to the DD star threshold, which has also been seen in other experiments since then and which is well established by now. And similar states have been observed since then, like the X3915, and especially the Z states. And these cannot be just CC bar because they carry charge, so they cannot be just germanium states. And the progress in these fields is also reflected in the number of reviews that have been written just in the last couple of years. Now, in fact, the oldest tetraquark candidates have been the so-called light scalar mesons. So let me start there. Here you see the light meson spectrum arranged with their spin and parity and charge conjugation parity quantum numbers and their flavor content. So each gray box here contains a full multiplet. The states made of light quarks, up and down quarks, are shown in blue color. The kaon-like states with one strange quark in green, and the SS bar states in red. So for example, here we have the pseudoscalar mesons, the pion, the kaon, the eta, and the eta prime, or the vector mesons, the rho meson omega, the k star, and the phi, and so on and so forth. And this list extends not only horizontally, but also vertically, because for each ground state, we can also have radial excitations. Now, if we go to the non-relativistic quark model, we can combine quarks and antiquarks to spin 0 and spin 1. And together with orbital angular momentum, this gives us the JPC quantum numbers and the mass ordering that we would expect in the quark model. So for orbital angular momentum 0, we have the pseudoscalar and vector mesons. For orbital angular momentum 1, we have the axial vector mesons and the 0, 1, 2++ states. And this is also how I ordered them here horizontally. And you can see that this mass ordering would be roughly realized if it were not for the light scalar mesons. So they don't fit into this pattern. The second problem concerns the mass ordering inside the multiplet. The blue states are made of light quarks, so they should be the lightest ones. The green states have one strange quarks followed by the SS bar state. So that's what we would expect to see. And we roughly see this in most of the channels here for the vector mesons, for the axial vector mesons, for the tensor mesons, with some goodwill even for the excited states. But the two channels where it doesn't work are the pseudoscalars and the scalars. Now in the pseudoscalar channel, we roughly know what's going on. We have spontaneous chiral symmetry breaking. This is what makes the pion especially light and the other pseudoscalars. And we have the axial anomaly, which gives an anomalous contribution to the eta and eta prime and pushes up their masses. But then again, what about the scalar mesons? The lightest state in this channel is the famous sigma meson, or also called F0 500, which appears as a resonance in pi-pi scattering. But in contrast to the rho meson, which gives a clear bump in pi-pi scattering, the sigma is just a very broad shoulder. So for a long time, it was not even clear if it is there or not. So it popped in and out of the PDG. In 2010, it was there again. It was called the F0 600, but with a large mass uncertainty from 400 to 1200 MeV. This is the blue rectangle here. So what you see is the complex plane of square root of S, so the momentum transfer in the S channel. So if we have a resonance, then it would appear as a pole in the complex plane. And then the real part would be quoted as the mass of the state, and the imaginary part is half the width. So the blue rectangle is what the sigma used to be. This was essentially an average over different measurements and pole extractions. And then with the help of dispersive analysis, it was possible to pin down the pole position of the sigma quite precisely to about 450 MeV. And this is the small rectangle that you see here. This comes from Roy equations, which are coupled channel partial wave equations, and which allow one to constrain experimental data by other experimental data in crossed channels based on general S-matrix principles like unitarity, analyticity, crossing symmetry, and essentially without any model input. So after that, the PDG decided to also narrow down this mass region. They now quote the larger rectangle here with a mass region of 400 to 550 MeV, and they also renamed the state to F0 500. There's also progress from lattice QCD. They are doing pi scattering and use the Lucia method to extract phase shifts and determine pole positions in the complex plane. But then again, none of this really tells us what the sigma is. It just tells us that it appears as a pole in pi scattering. So to better understand it, we still have to look at its multiplet partners. So here again the masses of the states within the multiplet. If they were QQ-bar states, then the isotriplet A0 and the sigma, they should be mass degenerate because they consist only of light quarks, followed by the kappas with one strange quark and the F0 as the SS bar. But as you see, this doesn't work out at all. So the A0 and the sigma are not mass degenerate. Instead, the A0 is almost mass degenerate with the F0, which doesn't make a lot of sense. Also, the decay widths are very different. The sigma and the kappa are broad states, whereas the A0 and the F0 are relatively narrow. And again, why are they also light? What if they were tetraquarks in the sense of diquark-antidiquark? This was proposed a long time ago by Chaffee. Turns out that also in that case, you end up with a nonad of states. If you combine a scalar diquark with a scalar antidiquark, you get 9 states. But now the mass ordering is reversed. Now the sigma would be the lightest state made of 4 light quarks, followed by the kappa with 1 strange quark, and the F0 and the A0 with 2 strange quarks. So this would immediately explain the mass ordering. It would also explain the decay widths, because the F0 and A0 sit close or just below the kk-bar threshold, so they cannot decay, whereas the sigma and the kappa sit above their respective thresholds in pi and kpi. So the sigma, for example, could just fall apart into 2 pions without even exchanging gluons. So it would be a broad state, which is hard to detect. An alternative explanation would be in terms of meson molecules. As I said, the sigma appears as a resonance in pi scattering, the kappa and kpi scattering. So they could be dynamically generated resonances. The A0 and F0 sit at kk-bar threshold, so they could be kk-bar molecules. And in fact, there is a large history of support for the non-QQ-bar nature of these states from a variety of approaches. So the question is, what can we say about the issue? Well, we can solve the Fourbody equation. So here it is. Now we have 4 independent momenta in the system. You can imagine that gets out of hand pretty quickly. From 4 momenta, one can construct 9 Lorentz invariants, plus 1, which is on-shell. 256 Dirac tensors, if you have 4 Dirac indices, and color and a flavor structure. So this is pretty much impossible to solve without approximations. So what we did was the trick that I mentioned earlier in connection with the mu and g-2 problem. We grouped these momentum variables into multiplets of the permutation group S4, because in that way we can switch off bunches of variables without destroying the symmetries of the problem. So here we end up with 1 symmetric variable, which carries the scale, which is a singlet. The triangle here lives in 2 dimensions, so it contains 2 variables. This tetrahedron lives in 3 dimensions, so it's a triplet, it contains 3 variables. And this is a ball, which also lives in 3 dimensions. So we have 3 plus 3 plus 2 plus 1 is 9 variables in the system. And now what happens is quite interesting. So now we solve the Fourbody equation and we switch off everything except the symmetric variable. And the sigma mass we get out of that is about 1500 MeV. That's roughly 350 MeV times 4. So it's about 4 times the constituent quark mass, which is what you would expect if you put together 4 quarks. Now, if we switch on the triplets, this triplet doesn't change anything, so we can immediately get rid of 3 variables in the system. The second triplet does change something, but the huge effect comes in when we switch on this doublet here, because then the mass drops down by a factor of 4. So the important momentum dependence lives inside this triangle. And here you see why this happens. This is basically like a Dalitz plot of the Bethe-Salpeter amplitude inside this triangle. Each side of the triangle corresponds to one of the possible two-body clusters, or isobars, if you want, in the system. So if you have quark, quark, antiquark, and antiquark, you can combine them in 3 ways to two-body clusters. You could have a diquark-antidiquark, which lives on the upper side of the triangle. You could have a meson-meson clustering in 1, 3 and 2, 4, which lives on one side, and another meson-meson in 1, 4, 2, 3, which lives on this side. And what you see here are the effects from the pion poles in the system, which are outside of the integration region, but they're close by because the pion mass is so small. So the system, what happens is that the system dynamically develops pion poles in the solution process, even though the equation doesn't know anything about pions. It's just quark and gluons. So in that way, a four-quark system effectively looks like a meson molecule. And these are our results. So the boxes here are the PDG values for the sigma, the kappa, and the A naught and F naught. And the bands are our results around the light current quark mass. So we are qualitatively in the same region. And by the way, this also explains why the light scalar mesons are so light. The problem with the diquark-antidiquark interpretation is that a typical diquark mass scale for a scalar diquark is 800 MeV. So if you put together 2 diquarks, then you have 1600 MeV minus some binding energy. Why would the resulting state end up at 400 MeV? Well, if the dominant internal degrees of freedom are not diquarks but mesons, then it's clear, because the lightness is simply inherited from the pseudoscalar Goldstone bosons, the light pions and kaons, on which the system depends. Okay, in a similar way, one can describe clusters also in four-quark states. So now I'm returning to the exotic states in the heavy light sector. Imagine if you, for example, if we have a CC bar, QQ bar system, then there are also 3 ways how this can cluster into a two-body system. We could have a meson molecule in terms of 2 heavy light mesons, CQ bar and QC bar. We could have a hydrogermanium in terms of a heavy CC bar and a light QQ bar. And we could have a diquark-antidiquark system in terms of CQ and C bar, Q bar. Now there are various models on the market which try to explain, for example, the X3872 or the ZC3900 in terms of either of these configurations. In the four-quark equation, they all mix together. So if any of this is dominant, we can figure out which one is dominant. And that's what I'm showing here. So now I'm showing the masses, the mass in the X3872 channel, so in the 1++ channel, as a function of the light current quark mass. So we keep the mass of the charm quark fixed, and we vary the light quark mass from the chiral limit to up and down quarks to strange quarks to charm quarks. So on this line, we would have an all charm system. Here we have a CC bar, SS bar, and here we have a CC bar, light bar. So the experimental state would sit on this line at 3.872 GeV. And now I study all these 3 configurations separately to begin with. So the DD star, the meson molecule is shown in red. This would correspond to a DD star here. The hydrogermanium is shown in blue. This would correspond to omega J psi. And the diquark-antidiquark is shown in green. Now, before you look at the data points, look at the lines. These are just the thresholds of the respective systems. So the green line is the sum of the scalar and axial vector diquark masses. The blue line is the sum of omega and J psi masses. And the red line is the sum of D and D star. From there, you already see that the diquark-antidiquark threshold is much higher. So this would mean it becomes more unlikely that the system is dominated by diquarks. And from the actual results, you see that there is binding in the diquark channel. So this is the actual masses are below the threshold. There is repulsion in the hydrogen channel. So the blue points are above the threshold. And there is again attraction in the molecule channel. So the red points are below the threshold. So the molecule produces the lightest mass. And then in the end, if we combine everything, so we start with DD star, then we add omega g psi, and then we add the diquark, everything falls on the same line, which means that the DD star was the dominant component. And we find the same for other quantum numbers in the CC bar QQ bar channel. So in all these cases, we have a strong meson-meson component corresponding to this molecular-like configuration, which for these states would correspond also to DD star. The exception are CC Q bar states, where so far there are no experimental candidates, but here also diquarks could play a role. Now a natural question is what happens if we go from 4 to 5? Because right now we also have pentaquark candidates in the heavy quark sector, which also sit close to thresholds. Sigma C and D or sigma C and D star thresholds. So these are the LHCb pentaquarks. So they also look like molecules. The question is, can we also describe them? Can we apply our methods? Well, yes, you see Madalena is on it. So she's a master student and she is currently busy setting up a coupled channel two-body approximation of the 5-quark equation. So stay tuned. And then what happens if we go to 6 quarks? If you remember the statement about the tetraquark, then this would be pretty much also the mechanism that could explain the transition from quarks and gluons to light nuclei. Imagine I put together 6 quarks and let them interact by gluons. And then the system dynamically produces nucleon poles. So that would, for example, for a deuteron, would be at the same time a 6-quark state, but also a molecule of 2 nucleons. But in that way, one could also study if there are other configurations beyond nucleon-nucleon that contribute to such states, like hidden color configurations. One could study exotic dibaryons and hypernuclei, and also short-range correlations. For example, if the EMC effect is due to overlapping nucleons and nuclei, then this would be pretty much the way to study it. A closely related problem is the origin of the short-range nuclear force. In nuclear structure calculations, the repulsive short-range part of the potential is either parameterized or it comes from contact interactions. So the question is, what is its microscopic origin? If I break up the NN scattering amplitude into quarks, then I will get a diagram like this, where this box here is a quark-antiquark scattering matrix. A quark and antiquark can dynamically produce internal meson poles. So this would produce automatically a pion exchange between 2 nucleons, which would correspond to the attractive long-range part of the potential. But it would also produce gluons, which contribute to the quark exchange, which could be responsible for the short distance part of the potential. So this gives us a window from QCD to nuclear physics that we are very excited about to explore. All this is also tied to the question of resonances. Most hadrons are resonances and decay, which means they correspond to poles in the complex momentum plane. So what we see, the bumps that we see in an experiment are the remnants of the poles in the complex plane of a scattering amplitude. Actually, it is surprisingly difficult to get something like this out of a Bethe-Salpeter equation made of quarks and gluons, because what you need are internal hadronic degrees of freedom. For example, if a rho meson decays, if a rho meson fluctuates into pi, then the pion poles would produce a threshold and a cut structure, so that the rho meson actually becomes a resonance. And this can only happen beyond rainbow ladder. And it comes with a number of complications, because if we have a threshold in the system, we can no longer go beyond it without taking the poles into account. Here we solved a 4-dimensional scattering equation using contour deformations, which are a promising way to address this problem. What you see here is the complex plane of the integration momentum, of the loop momentum here. we're supposed to integrate from 0 to infinity, but we cannot because the cuts here coming from the poles in the loop, they block the way. So if we would just integrate over that, we would get the wrong result. So what we did is we looked at all the possible configurations that these cuts can produce and designed according contour deformations. And in that way, we can solve the scattering equations in kinematic regions that would otherwise not be possible. So in particular, we use a Euclidean metric, but once we do things in the complex plane, this is equivalent to going to Minkowski space. So one can show that the scattering amplitude is the same in Euclidean and Minkowski space. I should also note that this is a 4-dimensional scattering equation without the usual 3-dimensional reductions that are made in the literature, so this could also be extended to coupled channel calculations. Now in the end, I will briefly address one final topic, namely hadron structure calculations. I already mentioned form factors earlier, but these days people are talking about tomography of quarks and gluons inside the nucleon and 3D imaging. For these things, we have to study generalized pattern distributions, transverse momentum distributions, which are extensions of the PDFs, which contain the longitudinal momentum structure of the nucleon and other hadrons. There is a systematic way to derive how external currents couple to a hadron, which I'm showing here, for example, for nucleon Compton scattering. So we have 2 photons that couple to the nucleon. So basically all the ways how the photons can couple to the quarks inside the nucleon. From here, you can identify diagrams that might look more familiar. For example, the internal nucleon resonances that are generated in this process would come from this diagram, because this 3-quark scattering amplitude can produce all intermediate nucleon poles, whereas the handbag diagrams would come from here. So this would be the way to extract PDFs, GPDs, and TMDs. This is an area we are only beginning to explore. Recently, we derived the tensor basis for the Compton scattering amplitude in terms of 18 Compton form factors, which are free of kinematic constraints. From there, one can extract polarizabilities, one can go to different kinematic limits, like deeply virtual Compton scattering. Just to give you an idea, here we projected the nucleon resonance contributions from experimental data onto these 18 Compton form factors. Each color stands for a different resonance. So this would be the delta resonance, the Roper resonance, and other resonances. Now, each of these Compton form factors depends on 4 variables. How do you visualize a data set in 4 dimensions? Well, this combination of permutation group tools and tensor bases essentially does the job, because from here one can identify a scaling variable. Then the bands here still contain the full 4-dimensional momentum dependence, but effectively they collapse into narrow bands, which just depend on this scaling variable. So if you know the amplitude in one particular kinematic limit, you already have a good idea what it would look like in a different limit, like DVCS. All right, with that I come to an end. Here's just an advertisement for our spectroscopy program at the INT in Seattle. Originally it was designed as a 5 weeks program, but now due to the COVID situation, we restructured it to a 3 weeks online program, and maybe with a live workshop on a later date. The fact that it's online means that anyone can participate, so we would be happy to see some of you there if you're interested. Okay, thank you.
Okay, thank you very much, Gernot, for this very nice presentation, very clear on this very complicated subject. So now we have some time for questions. Please raise your hand or just open your mic.
Yes, sorry.
Okay, so go ahead.
Hi, Gernot. Nice presentation, really, really nice, thank you. I have a question on the exotic states that you mentioned. So on your slide 22, I guess?
32?
22.
22.
Yes.
Yeah.
Yeah. Just a question. So the quantum field theory, you work on. I don't know if you work directly on this or not, but in principle, the equations that you use to calculate this is in momentum space, right?
That's right. Yes.
Could you change this? I mean, would you be able to calculate this in coordinate space as well? Assuming that you have, for instance, an external source at fixed temperature. So let me try to explain my question. So I'm not so sure if you are familiar with the latest measurements on these X states in heavy ions. And so there are some evidence that we see these states in the presence of when you collide light nuclei. And the results are quite interesting. So you see an enhancement of this state when compared to the proton-proton case. So in proton-proton, when you increase the multiplicity, or in PLED, let's say, when you increase the multiplicity of your event, you see a depletion of this state with respect to the bound state. And in heavy, for instance, from the latest results from CMS, it seems that there is an enhancement. It's still not very conclusive, but it seems there is an enhancement. And my question would be, if you are able to calculate using the same formalism that you used to address its non-perturbative effects and the mass effects on the presence of an external source. In this case, some quark gluon at fixed temperature. Would you be able to calculate this? So that's why my question, if you are able to cast this in momentum space, which would be the most indicate to do this kind of.
Well, I mean, okay, so I would not do this directly. I would not start in coordinate space, let's put it like that, because everything is, of course, a much more complicated.
Yeah.
So
I know.
It's crazy. I mean,
I know. We have the same problem for even when addressing PQC. So yeah.
But of course, what we can do is do Fourier transformations at the end, right? So once we calculate the systems, we can go to coordinate space and look what these things would look like in coordinate space, right? I mean, that's probably not exactly what you have in mind.
Well, that would be a first start. Of course, that for us it would be more interesting to see with some source that it's evolving in time. But in any case, the first exercise, of course, would be to consider just the fixed temperature source, let's say, and consider the naive exercise of having some fixed length medium, let's say. I mean, and in this case, yeah, the Fourier transform probably works. Okay.
I mean, the second point is, of course, when it comes to fixed temperature, there is maybe a lot more that we have to do before doing such kinds of calculations, right? So we are just getting there in describing hadrons at fixed at finite temperature and density. So I think there would be some other areas which we should explore first. But I mean, yes, Christian Fischer in Gießen is very interested in these topics also. So,
okay.
So there is certainly a chance to to look into it in the future. Yes.
Okay, that would be really interesting. Thanks.
Thank you. So now we have a questions from Nuno.
Yes. Hi. Can you hear me?
Yes.
Okay. Yeah. So Liliana did mention about this result of the X in heavy ions. So and she put it carefully. So we see a hint of an enhancement, but we will continue studying it, and we've talked about this before. But now I wanted to also ask you still about the X3872. So as you know, so there's a bunch of new results on the X. So we are doing quite a bit of work on that. So LHCb, for example, has just 2 papers, one on the mass and the width of these particles. And one result that we also have from CMS, just very recent, is basically we are measuring this now in proton-proton collisions, but in decays of the mesons. And we have observed and reported this last week, the BCBS decaying into this X plus phi. So, and my question is, I mean, in your studies for disentangling the nature of this particle, there's information like, in addition to the mass, like the width and decays from other hadrons, could it be helpful?
Yes, absolutely. So that would be the way to go forward. That was, well, unfortunately, the student who was mostly working on this now finished his PhD and left physics. So we have to find another person to continue this trend. But I mean, yes, that was the plan. So he already tried to get a width out of it. In principle, that could be done directly from in the way we do it anyway. But this ties into this question of how to address resonances in the complex plane. So for that, we need this contour deformation technology stuff. But yeah, that would be the next step to describe the width of the state, the various decay channels, etc. Yeah. So that's certainly on the agenda.
Okay, very good, thank you.
Okay, more questions? Liliana again.
Sorry, just one more question that I had also here. Slide 9, I guess, or slide 8, I don't remember. It's just a curiosity. So you have here the comparison of your results with lattice. One thing that lattice can do is actually to decompose the mass into the several components, right? Light quarks, joint quark gluon energy, or only pure gluon energy. Are you able to also to do the same?
Once we can calculate the corresponding objects, which are the PDFs, well, the GPDs actually, then yes, we could do this too. I mean, about these decompositions, I mean, you know these pie charts, yeah, where there's a contribution from the gluons and the quarks, etc. For me, it's not entirely clear how these things are really cleanly separated in a gauge invariant way, but apparently, so yeah. Anyway, the answer is yes, in principle we can do it, and that's the plan also. So once we can calculate structure, once we can do the structure calculations, calculate GPDs, then we can extract it from there. There have been actually simpler calculations in the NGL model. So the NGL model is basically, I mean, you can reduce this to an NGL model if you just contract the gluons to a point. And then you can do all of these structure calculations in a similar way. So and there are some results from there, which look actually quite good. So they compare well with lattice also.
And I'm not familiar with these results. So they are in agreement with the lattice?
More or less. I mean, the NGL is of course a very rough approximation, but yes.
Yeah. Okay. Thanks.
Okay. I'll boost my power, and I'll ask you also a very naive question. In your slide 6, you're close by. Damn, no, 12. Sorry, 12. Yeah, 12. So you said that you have a close result here, but you have a very large theoretical error in this calculation. What's driving this error?
This error here is really, so what you see, the band here, that's really just the sensitivity to this interaction. So that's exactly the same band that I show here. So it tells you how sensitive the results are to the quark-gluon interaction.
Okay.
Now the thing is, once we go beyond rainbow ladder, there is no such interaction anymore because everything is really calculated. So there is no model input anymore. And that is sort of the next frontier here. So to do beyond rainbow ladder calculations, not only for spectroscopy, but also for structure. So that would be the next step to calculate form factors. Well, but one of the next steps to calculate form factors beyond rainbow ladder also. But I mean, well, you call it a large error. I would say this is...
No. I was surprised because the error is bigger than the experimental error. That's
sure. I mean, I'm dividing here by the dipole, right? So this is not the form factor, but divided by the dipole, so to magnify what's really going on.
Yeah.
Well, I think that's the best one can get so far. But okay. I mean, there is a truncation, right? So there are approximations in the game. I mean, you cannot expect to have a super precise result.
Yeah,
that's just the first level to be improved upon.
Very well. Okay, any more questions? Okay, it doesn't seem so. Okay, so once again, Gernot, thanks a lot for this very nice seminar. The slides will be available, and Gernot was very nice to allow to record also this seminar. Next week it's a national holiday, but the week after we'll have Sofia Andringa, and she will talk about the neutron measurements done in Snowplus and Tune. Okay, thank you all, and see you.
Thank you.
Bye.